Hello, everyone. I'm happy that you took the time and interest in attending our talk. My name is David Cerdeira. I'm currently a PhD student studying under the supervision of Professor Sandro Pinto. This work was done in collaboration with José Martins, a PhD student, and all three of us study at the University of Minho in Portugal. Study and Professor Santos, Professor Pinto teaches. This work was done in collaboration as well as Professor Nuno Santos from IST Lisbon, who is also my co-advisor. Let's begin. TrustZone was introduced nearly 2 decades ago in 2004. Today, TrustZone is still present in commercial off-the-shelf platforms and in ARM Cortex application processors. TrustZone has been leveraged to build TEEs in billions of mobile devices worldwide. These TEEs support applications ranging from biometric authentication, digital rights management, and electronic payments, for example. To better understand TrustZone, let's start by taking a look at the TrustZone software architecture. TrustZone is centered around the concept of protection domains named normal world and secure world. The normal world hosts the rich OS, which is typically Android, and this OS will feature a driver to interact with the secure world. This interaction is to request secure services. The secure world hosts the trusted OS and trusted applications which implement these services. Each physical core provides 2 virtual cores, one normal and one secure. To switch between them, there's a layer of software called a secure monitor, and this layer performs a secure context switch between these states. The normal world can't access any secure world resource, and this is to serve the main purpose of TrustZone, that is to prevent trusted applications from being compromised by a potentially malicious rich OS. However, TrustZone has some major problems, and in particular, there have been many security-critical vulnerabilities, mainly to one architectural flaw, the excessive level of privilege of the TE. More specifically, the trusted OS has unrestricted access to the full system. TrustZone flaws have allowed attackers to mount attacks that, from the normal world, are able to compromise a TA, from that compromised TA, compromise the trusted OS, and once in control of the trusted OS, an attacker can compromise other parts of the system. The normal world, other security-critical TAs, and the highest privilege piece of code, the secure monitor. Our goal is to fix this excessive level of privilege. And we intend to do this by deprivileging the trusted OS. By deprivileging the trusted OS, we can increase protection for the normal world. We can extend the secure world to host multiple trusted OS and trusted applications, offering better protection for trusted applications. And we can protect the secure monitor. And of course, we can extend these properties to all zones that we instantiate. So we propose ReZone. With ReZone, we make the following contributions. An approach to deprivilege the trusted OS. We use TrustZone orthogonal hardware features present in commercial off-the-shelf platforms. We implement ReZone in a real-world platform and software stacks. We evaluate ReZone running in the physical platform, running embedded Linux and Android. Our performance analysis concludes that the ReZone does not significantly degrade the user experience. And we surveyed 80 security-critical CVEs, and we conclude that ReZone can help mitigate 87% of them. Let's take a quick look at the software and hardware components needed by ReZone. This is a typical TrustZone software and hardware stack, including a TrustZone controller that is used to perform access control to normal world and secure world memory. The first piece of the puzzle is that we must introduce logic to the secure monitor. This is needed because we need a specific way to enter and exit zones, and we must do so securely. Second piece is what we call a PPC, a platform partition controller. The PPC is typically used to perform access control of system resources to other bus masters, which can include the GPU, for example. And in our case, we use the PPC, we leverage the fact that the PPC stands between the processor core and the memory, allowing us to enforce our access control policies. Second hardware component we need is what we call an ACU, an auxiliary computing unit. This ACU is a companion processing unit that is nowadays ever more present in SoCs, and these ACUs can be leveraged for a variety of purposes. In ReZone, we use it to execute the gatekeeper. Trampoline and gatekeeper coordinate between themselves to securely reconfigure the PPC. This is important because we don't want to give the processor core direct access to the PPC. One last piece of the puzzle is that the PPC should be able to establish different domains for ECU and for processor core. This is to allow us to establish different access control policies for the processor core and for the ECU. By using the PPC and the ECU together, we can deprivilege the trusted OS and thus achieve our proposed goals. Let's take a quick look at how the PPC and the ECU are used together. Keep in mind that these are not the full details, just a simplified version. So, starting from normal world execution, the normal world accesses normal memory, and it is prevented by TrustZone, as in typical systems, from accessing the secure world. On a zone entry, the trampoline coordinates with the gatekeeper to securely reconfigure the PPC. Again, we don't want the processor core from accessing the PPC controller directly. And so the gatekeeper will actually validate interactions from the trampoline and reconfigure the PPC on its behalf. After the context switch, a zone will execute, and the PPC will ensure that that zone will only be able to access that zone's memory. On an exit, again, the trampoline and the gatekeeper coordinate themselves again to securely reconfigure the PPC in a similar way as to when the zone was executing, was on an entry to the zone. And after all this, the normal world can resume execution. Implementation of ReZone is quite nuanced. And without going over details, these are the main implementation challenges. Cross-core synchronization, where we use synchronization primitives and we suspend all cores in a cluster except the one executing a zone. We must perform microarchitectural maintenance, cache, and TLB. We optimize the reconfiguration of the PPC, and we handle non-obvious aspects of exiting a zone, preventing crashes and potentially cache code injection. If you are interested in details, I invite you to take a look at our paper. Now for the evaluation. We evaluate the performance of ReZone across 3 vectors. Microbenchmarks, where we evaluate the REE-TA interactions granularly. We evaluate the performance of ReZone across 2 TAs that implement real workloads, and we evaluate the impact that ReZone has on a system when it interrupts normal workloads. For microbenchmarks, we evaluate Opti's Xtest test suite and the global platform client API. For the real-world use cases, we evaluate a Bitcoin wallet TA and the DRM TA and its application. We make 2 main observations from these tests. The first one is that simple workloads with many world switches will incur higher overheads. If you could take a look at the bars highlighted in red, these showcase exactly this scenario where we have many context switch and the workload is quite small. Without ReZone, this workload takes 5 milliseconds to execute, and with ReZone, the overhead is over 3 times. However, highlighted in green, we have a workload that makes less context switches, and the execution time is much longer. And in this scenario, the overhead with ReZone is only 1.25 times. Our second conclusion is that the user experience is not significantly affected. This graph showcases the elapsed time between video data processing events in the case of the DRM application, and as you can see, the impact is quite small. The last piece of the performance evaluation is the impact on normal world. For this, we evaluate the benchmark PCMark 3.0 for Android. And we test 2 scenarios. The first scenario, we use 1 single core and interrupt the workload at high frequencies. And as you can see, the worst case for ReZone is when the frequency is at 10 milliseconds, causing an overhead of 13%. The second scenario, we wanted to test a scenario where multiple cores try to execute a zone at the same time. And in this scenario, we involve multiple cores interrupting the workload at 1-second intervals. And as you can see, the worst case scenario is when all 4 cores are trying to execute a zone simultaneously. And in this case, the penalty for the benchmark is nearly 4%. Now, for security evaluation, we, in the paper, actually make one theoretical one and one CVE mitigation. I'll only present the CVE mitigation. We've gathered 80 security-critical CVEs and tried to assess how helpful ReZone is at mitigating them. We don't have enough information about some of them to make this assessment. We make an assumption that there are multiple zones executing in a system and there's 1 TA per zone. We conclude that ReZone can help mitigate nearly 87% of them, meaning that we can mitigate most trusted OS and trusted application vulnerabilities. However, ReZone doesn't mitigate against secret disclosures, hardware attacks, cryptographic flaws, or bootloader flaws. Lastly, we wanted to assess how widespread ReZone can actually be, given that it requires some specific pieces of hardware. We surveyed 19 platforms, and we conclude that ReZone can actually be deployed on 13 of them. We'd like to note that many Qualcomm platforms can actually support ReZone, meaning that ReZone could potentially be deployed in billions of mobile devices worldwide. To wrap up, TrustZone TEEs have architectural flaws. ReZone is a novel security architecture that reduces TE privileges. ReZone leverages TrustZone-agnostic hardware primitives. We implement and evaluate ReZone in real-world platform and software. Our evaluation showcases that the user experience is not significantly affected, and we conclude that ReZone can help mitigate many high-severity vulnerabilities. Thank you for your attention. I'll now be answering some of your questions.